Good morning.
Good morning.
Good morning, everyone.
Good morning. Good morning.
So, well, everyone, this is Ollie's Defense, and welcome, to this event. I see that everyone that I have seen so far has they're on mute, except a couple of people. So if you could put yourself on mute, that would be great. Now, that's right. And so what we're going to do is we are going to, I'd like to have Ollie go through the presentation. And if anyone on the committee has a question, and they can unmute and ask that question, a question relative to, a clarification or something of the slide. But we'll hold the questions until the end, and then I'll open it up. But what I'd like for anyone who's not on the committee to do would be send me a message via chat that you'd like to ask a question, and then I will recognize you, and you can ask your question. And then after we finish this, then everyone can leave, and we'll have a further discussion with the committee. So I think people are still joining, and hopefully that's okay. All right, so I'm going to stop my video, and maybe everyone else can as well. And we'll go ahead, and Ollie can share his screen.
Okay, thank you, Dr. Crawford, and hello, good morning, everybody. I'm gonna stop my video, so I'm sure that this can be fine. Okay. So I'm gonna go over the problem and the objectives. Then I will be discussing data description and experimental design. Then I will go over chapter 2, where we had investigated feature extraction and also predictive models based on remote sensing data. Then I will go on chapter 3. In chapter 3, we added genomic and weather data to the predictive models. And also we had multi-year predictions. And finally, in chapter 4, we had investigated the use of deep learning for both feature extraction and also predictive models. So we know that plant breeding, the goal is to produce genotypes with a specific reason, for example, genotypes that can maximize the biomass. So for this producing, we need to have, we first produce so many genotypes, then we select the best ones. This selection is done based on traditionally based on measuring phenotypes. And we know that a phenotype is the result of genotype by environment, by management practices. Phenotyping is required. However, it is expensive and time consuming to go to the field in a traditional way and measure traits such as biomass. So it's being said that the phenotyping is the bottleneck of plant breeding because everything else is less expensive and much faster. So our goal here is to reduce field-based phenotyping. In this study, I had 3 objectives. First, like I said, if the goal was to see if there is a clear relationship between remote sensing and the phenotype, specifically biomass. So for that, we did some feature extraction, extracted multiple features from LiDAR and hyperspectral data. And then we also evaluated different regression models. Then we added genomic data to the models. And finally, we used deep learning based predictions, and also for feature extraction, we used deep learning. So here's a review of the sensors and the platforms we used in this study. We had RGB data, RGB sensor, LiDAR sensor. We had hyperspectral, linear, and SWIR. And all of these sensors were integrated with APX, which is GPS IMU unit. So all the data that we collected was georeferenced. This is a field design for 2017. In 2017, we had 4 fields, 4 experiments. As you can see, for example, this is hybrid calibration panel. Here is a map that is generated basically by using RGB data. In this field, this experiment, we had 18 genotypes, and each genotype was replicated 4 times. So in total, we had 72 plots. This is the field design for 2018, where we had 5 experiments. And this is field design for 2019. We had 2 experiments. And this is more detail on those experiments. You can see we had 10, 12, 11 experiments. Some of them are hybrid lines. Some of them are inbred lines. We had different number of plots. Sometimes we had very few plots. Like here, we had only 72. And sometimes we had a lot more than that, 1800 here. And we had different planting, sowing, and harvest date in different years. And also for 3 of the experiments, here hybrid calibration 2017, this one hybrid calibration 2018, and test cross calibration 2019, we had multiple times biomass data during the season, as well as end of season biomass. So in the first chapter, our objective was to find the relationship and see if it's possible to reliably predict biomass using remote sensing data. So we extracted multiple features, and we evaluated also multiple regression models. I have presented this and discussed a lot in my prelim exam. So here I'm gonna go just show the final result in a couple of slides. So when we say remote sensing data, we have, for example, this image. We extract multiple features. First of all, we extracted all the features from only rows 2 and 3 to avoid border effect. And also we trimmed each row by 10 pixels or 40 centimeters from each side. We had hyperspectral data extracted, vegetation indices, integration features, and derivative features. And from LiDAR, we extracted multiple high percentile canopy cover, volume, and statistical features. So this is a results for experiments in 2017 and 2018. We had 9 experiments, and you can see that we get. So first of all, we had 3 regression models here to evaluated: PLSR, SVR, and random forest. And we had multiple data inputs: LiDAR only, linear only, SWIR only, linear plus SWIR, LiDAR plus linear, and all of them together. So we were looking at which data input will provide us how accurate predictions. So there are variation in the results, and the variations basically we group them in 3 categories. First of all, whenever we have more genotype in one field, we get better results. For example, in hybrid calibration 2017, we had low biomass and high biomass, so we get better R-square versus inbred calibration 2017. The other factor is number of samples. For example, in SPDIF 2017, we had a lot more samples than inbred calibration 2017. So we also here got better results, even though genotypes are very similar. And finally, one reason that we get not good results sometimes is that we have genotypes that they are very different. For example, in BAP 2017, we had some genotypes that they never flower, so they always grow until the end of season. So they were really tall, like 5 feet or even more. And some of them were short and low biomass. So in that situation, if your test and train data, they are not very similar, then you get not as good as prediction as you would expect. The other The other problem that we were looking at was how many data sets do we need from each season and which time of season we should collect data. So here, this graph shows you, for example, I'm going on this one, June 29. So this one, first one shows the LiDAR data that collected only on that day, then SWIR, then linear, then all of the data that collected only on that day. So this red bar shows if you collect all this data in that one date, what accuracy you would get. And these four, they showed the same LiDAR, SWIR, linear, and all of the data from this date and also the dates prior to that. So you can see that if you look at individual dates, we can say that maybe here in July 3rd, July 11th, we get the maximum biomass accuracy for using only one date. And if we look at the cumulative ones, we can say that this one here, when we use all the data from the whole season, we got the maximum biomass. However, the difference here and here is not much. So I would say that we don't really need to collect multiple times or many times during a season. We should basically target the dates that are more important. So as a conclusion, as I said, we had reliable and accurate predictions based on when we used hyperspectral chemistry-based features from hyperspectral, geometric-based features from LiDAR, and we needed both of them to get high accurate results. We did some evaluation on the results of predictions, and we found that data source is very important. Its impact is significant, and also regression method is important. And finally, as I said, we found that individual data sets from DAS 55 to 75 days after sowing is very important for models. So in this chapter, we found that, okay, we can predict the biomass using remote sensing. Now we are looking at adding more data to the models, basically genomic information and weather data. So we looked at feature extraction and also developing predictive models based on that data. So with remote sensing, there are some challenges. For example, we know that the models are based on the data. So if you develop the model for 1 year, one experiment, it probably won't be accurate for other experiments or next years. The other type of predictive models is using genomic selection. So in that, they collect phenotypic data from a training population. They collect genomic data from the whole population. Then we develop the predictive models for the training population. And then we can apply these predictive models for the lines that they are genotype, but they are not phenotype. So we can predict phenotype. But if you look at this model here, it says that genotype by environment, by management practices will result phenotype. So if we are predicting phenotype only based on genomic information, we are not considering these two components. So as a result, we won't have accurate predictions, especially for low heritability phenotypes such as yield or biomass. So the question was, can we actually combine these two models and get better results? So from genomic information, first of all, we had around more than 80,000 markers. And we said that, okay, maybe we cannot have all of these markers combined with our remote sensing features because we have much fewer features in remote sensing. So if we have those many, they may not produce good results. So we looked at wavelets and wavelets in actually multiple levels, and also PCA components to just extract fewer features from all the markers that we had. So here you can see that wavelet in 6, 8, and 10 levels, and these are the inbred genotypes and hybrid genotypes. So basically, this wavelet in 8 level is kind of similar to wavelet in 6 levels. However, we have only fewer features. And here you can see the PC1 versus PC2 for inbred and hybrid genotypes. Another data source that we were looking at for especially for multi-year prediction was weather data. So we have here on right, you can see the weather data, precipitation, GDDs, and radiation for the 3 years, 2017, 18, and 19. So from this data, we decided to extract multiple features, 9 features. First, we divided the season into 2 groups, the data into 2 groups, before flowering and after flowering. And for each group, we calculate the average daily value of the 3 information, GDDs, precipitation, and radiation. So we have 6 features here. Also, we consider cumulative numbers at the harvest date for each experiment. So from each experiment, we have 9 features that comes from weather. And this is the result of our models. So we have the models that are remote sensing, genomic data, and weather data are included. The models are developed based on 2018 experiments, and we use SVR as a regression model here. And you can see that the biomass data, the biomass prediction here. So what you can see that, first of all, this R square that you can see here is 1-to-1 R square. And you can see that there is a bias between the predicted and the reference data. But like I said earlier, the goal in breeding is to just select the genotypes that produce the maximum biomass. So as long as we know that these genotypes here, they produce the maximum biomass, then we are fine. So what we did, we calculated the rank of each genotype in terms of biomass, which you can see here, and then calculated R square for that rank. So RMSE here, for example, is 9, which means we have around 9 error in ranking, and we had in total 120, 140 genotypes. So we can say that we have around 7-8% error in our ranking. And this was when we used only 2018 data for biomass prediction or rank prediction in 2019. So here we are using 2 years of data. We are using both 2017 and 2018 on the same models, the same data inputs. So you can see that the biomass prediction actually, the accuracy improved a lot, but the rank is more or less similar. And the reason is that 2018 and 2019, they are both hybrid genotypes that are more similar, and adding 2017, it does not help in rank estimation, but it does help in biomass prediction. So again, we are looking at others. Here we have more regression models, rich regression, PLSR, SPR, and random forest. We have various data sources. We have only genetics. We have genetic plus weather, remote sensing plus weather, remote sensing plus genetics, and all of them together. So the models here are developed based on only 2018 experiments, and then used for prediction in 2019 fields or experiments. So you can see that with the genetics and remote sensing, we are limited to around 0.5 R square, but when we combine both of them, we got much better accuracy. Random forest is a little bit different. We could be able to get better accuracy with genetics only, but when we add remote sensing, it doesn't really improve much, and we think that it's probably because of the fact that there are a lot of correlation between remote sensing features. So here are the same models, but these models now are developed based on 2017 and 2018. So that was only based on 2018. Now here we have models based on 2 years. And the same again. remote sensing, add weather data to remote sensing, it does not change much. And the reason is that we think that maybe remote sensing is already the result of environmental factors. So adding weather does not help here. And we have all of the data sources together, which we see we got the best accuracy again. Another thing that we looked at was to see if our feature extraction was appropriate. So we looked at having the same models, remote sensing plus weather, and using different genomic-based features, wavelet in multiple levels, using all the markers together, and using some of the PCA with different components. So again, the models are developed for 2018, 17 and 18 experiments and are estimating rank for 2019. So we can see that for most of experiments, when we use a wavelet in 4 or 6 here in SVR, we get the best results. Also, we can see that with PCA, we got good results with SVR, but with other regression models, we didn't get good results with PCA. Finally, we looked at prediction in terms of time, like how early we can predict end of season biomass or the rank of biomass for 2019 using the data from 2017 and 2018. So here you can see that for the 2 experiments, random forest provided the best accuracy when we are using only one data set. And that's, again, the same thing that I said earlier, because we don't have very correlated features when we are using only one data set, so we can get good results with random forest. But as we add more dates to the models, we see that the random forest accuracy drops. But all the other 3 regression models, they improve when we add more data set, which is expected. The best model here, based on these 2 figures, we can say that SVR did best. It had the best accuracy when we had only one data set. And also another point is that maybe here or here we can say that we could estimate rank of biomass very well, and we don't really need to wait until the last date. So as a summary, I would say that first of all, the models were able to predict rank of biomass, I would say, well. For even the 2019, we didn't have any sample data from that year in our models. We also found that wavelet in 4 or 6 levels was providing good results. And also, like I said, we don't really need to wait until the last date, until the end of season for the last year. We could predict rank of biomass much earlier. So in our last chapter, the goal was to look at the features and see if we can extract features. First of all, if we can reduce the number of features using deep learning, and then if we can extract more features or different features. And also we looked at using more advanced predictive models based on deep learning. So we know that deep learning, it can produce better results mostly because it can look at the data in more depth, and also it can add more complexity to the model. But in remote sensing, we have a couple of challenges. For example, we have very big data in remote sensing. We have hyperspectral data. We have so many bands there. And also, we usually have limited number of sample data in remote sensing. So as a solution, we thought that, okay, maybe we can do the feature extraction and prediction in 2 different networks, in 2 steps. First, we look at feature extraction, extract some features that it can be done unsupervised. Then now we have have 272 bands here. Then we extract more features from those bands. And here we can have multiple layers. And finally, the end of this part of network, which we call it encoder, we encode only a few features from all the input layer or input features. So these encoded features will be considered as the reduced features or the learned features. And if we look at this part of network, is basically symmetric with the other part of network. However, if you look, we are extracting features, we are reconstructing features from only these 4 features. So it means that these features here has to be kind of the abstract of all the features. The same thing here, the only difference is that we are using convolutional layers, so it can learn the relationship between the features. Here we are not looking at the same time in multiple features, but here we are looking in multiple features at the same time. And finally, our reconstructed features will be similar to input features in our training. So we use the first network based on fully connected network, FAEN, and train it for 2017 hybrid calibration experiment. We trained it on the same experiment data. So you can see here, this is one example plot from that experiment. So these are the original features, and this is the reconstructed features, which is very similar to the original features. And we can see here the RNNs is less than 1%. And these 4 features are the 4 features that extracted for each data set. We had 4 data sets. And then when we use these features for all the plots in SVR models, we got this R square. So we did the same thing for the same experiment here. However, we trained the network, the feature extraction network, on another experiment. We trained it on Predictive test cross 2018. So if you look at the original features are the same, or from hybrid calibration experiment. Then we have reconstruction based on the network that was trained on Predictive test cross 18. So the RMSE here is a little bit higher than here, which is expected again because this data is not in the trained data. And the features extracted based on this network was different than the other one. However, the prediction accuracy is not much different than the previous one. So this was feature reduction. Then we look at feature extraction. We said that, okay, let's have the original data, hyperspectral data from one plot, which, like I said before, we are using rows 2 and 3. And then we have a few layers, a few convolutional layers, and then encoded features, and then another convolutional layers. We have here 2D convolutional layers, and we can extract features from whole image. So we trained that network on SPDIF 2018, SPDIF test cross 2018. We also trained it in supervised and also unsupervised mode. I said unsupervised. Supervised means that we add one more option to cost function. We say that, okay, the extracted features must maximize the correlation between them and the biomass, the end of season biomass for the experiment that is being training on, which is SPDIF test cross 2018. So here we have then we use that network to extract the features for all the other experiments. And we can see here one example plot from each experiment. For this SPDIF test cross 8, we have training and testing on the same experiment. But for other experiments, we can see that the network was trained on SPDIF test cross 2018, but used for other experiments. And we can see that the the reconstruction here is not really much different when we used it for other experiment if we compare this row. And then if we compare this row 2 and 3, row 2, they are the result of reconstruction in unsupervised mode, and row 3 is reconstruction in supervised mode. We can see that unsupervised slightly provided better results in terms of reconstruction because the reconstructed image is more similar to the original image. And then we used the we repeated the same experiment multiple times. We trained it on multiple experiments. Here, this on the top show where we trained the network, and then here shows where we tested the extracted features and used the extracted features to predict end of season biomass. The blue shows unsupervised training and green shows supervised training. So there are a couple of points here. First of all, we were able to train the model only on, for example, hybrid calibration 17 when we had only 72 plots. So I would say that the network doesn't really need much or many sample data. And also for hyperspectral here for biomass, we found that if we use the network in supervised mode, we could get better results. The highlighted one shows the maximum R-square for each experiment. For example, here shows that for hybrid calibration 2018, we got the maximum R-square when we trained the network on hybrid calibration 2017, which is kind of expected because they both are the same genotypes. However, they are from different years. And then we looked at using basically proposing the same kind of concept for LiDAR data to extract a few features from each plot. Here again, we are looking at extracting features from the whole point cloud from each plot. So we decided to use RNN, recurrent neural networks, basically because first of all, they are widely used for sequential data and they are very strong in finding the relationship between multiple inputs. So an RNN-based autoencoder basically is consisted of two parts of network. The first part, like before, it's the encoder, which I'm showing here. It's basically a many-to-one RNN network where you have multiple inputs and then you have a couple layers of RNN. It can be LSTM cells, and then you have the output. You have only one output from all the inputs. So that's why it's called many-to-one. So this is the encoder, and this output here will be considered as the encoded or the learned features. Then in the second part of the network, we have a decoder, which we get the input. The input is the output of the first part, the encoded features. And then again, we have multiple layers of RNN, and then we have inputs, but this time for each cell, we have one output. So this output will be representative of this input. So we try to minimize the difference between this output and this input, which we call it reconstruction. This is being widely used in text simplification. For example, you have one sentence here. Each word of a sentence is one input, and then for all of them, you will have only one label. So why are we using this in LiDAR data? The reason is that the words, when we use this for text simplification, we have multiple words. Each word doesn't mean much by itself, but they mean something when they are together in a sentence. The same thing here in LiDAR data. We have a lot of points that they don't mean much alone, but when we have them all together, they are representative of canopy, and we want to extract only a few features from the whole canopy, the whole point cloud. So this is a better representative of the network that we used. First of all, we put multiple points in a bag. The reason is that if we use each point as one input, we will have very long network, and we will have some problems in training in terms of training time and also gradient vanishing. So we put multiple points in a bag, and then we have the bags as input, like I said before. We have a couple layers of LSTM. Then we extract encoded features here. Then we copy them as many times as we had inputs. And the inputs depends on how many points we have in the number of input depend on how many points we have in a plot and how many points we put in a bag. So we copied the encoded features, and then we have a couple layers of LSTM, and finally we reconstruct the same bags. So here the only problem, or just to improve this, we decided to go with first of all, here in the second layer we put a couple, or we can choose this number actually, that have multiple inputs, multiple outputs of the first layer, combine them and consider them as the input for the second layer. So this way, in the second layer, we will have a less number of inputs. And also in the decoder part, we will have less inputs. So this will make the training much faster and mitigate the vanishing gradient problem. Also, we decided to try or evaluate non-symmetric encoder decoder. Here we can have only one layer of LSTM instead of two, so the training will be faster. So we evaluated multiple experiments using the first network and the second network. We tried both supervised and unsupervised. We also evaluated multiple number of layers or multiple number of different sizes for the LSTM layers, and also having different number of points in a bag. So you can see here, for example, for these two experiments from the first network and the second network, the number of points are the same in a bag, but the second network was much faster, like around 50%. I don't know how many percent, but it was much faster than the other one. So here you can see the results of using the first network for reconstruction. The network was trained on SPDIF test cross 2018 and was used for this experiment with the SPDIF 2017. So you can see the error in X, Y, and Z for all the 10, 24 points that we had. And also here you can see the features that we extracted for 4 data sets that we used we had in this experiment. And then here you can see the results of using the second network. If we compare these two, I want to point out that the axis is slightly different here. So if we compare these two, we can say that the features are different. However, the RMSE, the error in X, Y, Z for both networks is similar. But like I said earlier, the second network was much faster. And here we have the same RMSE in X, Y, and Z for all the plots. In SPDIF 2017, we had more than 1,200 plots, and you can see all the plots, the accuracy for that, the RMSE for that. For the plots for X and Y, we have around 20 centimeter RMSE, and for Z, we have around 10 centimeter. This one here, down here, this one is the data set on June 11. And because we had shorter plots, shorter plants, so the RMSE is also smaller for that date. And this is the same results using the second network. Again, the RMSE in X and Y is similar, around 17, 18 centimeter. And the same for Z, around 10 centimeter for later dates. So with this, I showed you multiple architectures. Here are a comparison. From hyperspectral, we found that if sometimes fully connected one and sometimes the convolutional one, they provided better results. But for one of the experiments, SPDIF test class 2018, we got the maximum R square from the predictions using the features extracted from these networks. The maximum R square here with when we extracted features from a 2D convolutional network. From LiDAR, we found that the first two networks that are basically feature reduction networks, they provided better results. And the reasons that we think that, first of all, we had very strong features. At the beginning, we had height percentile, we had canopy cover and canopy volume plus statistical features. So we extracted, we reducted or learned a few features from those features, and those features were very strong and highly correlated with biomass. So we got very accurate results here. On the other hand, here in these networks, we used all the point cloud, X, Y, and Z. And we know that for biomass, maybe X and Y is not that important. And if we were to only use Z, maybe we could have gotten better results here. So after feature extraction, we looked at having more advanced deep learning based prediction models. So we decided again to look at RNNs because we have multiple data sets from each season. We have multiple data sets in each season for each experiment. So, and it is important to find the relationship between these different data sets and how they impact the final biomass. So we proposed this network, which we have as input, we have weather data, LiDAR, and hyperspectral. We also can, for RNN cells, we can have either GRU or LSTM. We know that GRU is a simpler version of LSTM, and they both are able to avoid gradient vanishing. And finally, from each date, we have final biomass predicted here. So this is the results of using SVR, RNN, using RNN with GRU and RNN with LSTM. We trained the network on 3 experiments, and also SVR on 3 experiments, trained on SPDIF 2017, SPDIF test plus 2018, and SPDIF test plus 2019. And you can see the results here. I have highlighted the maximum R square for each experiment. So first point is that we got better results using RNN. With RNN also we got better results with GRU because, as I said, it is a simpler version of LSTM, and when we use these multi-year predictions, it sometimes is better to have simpler network because you avoid overfitting. And with LSTM, for example, here with SVR, we got the better results here. But I want to point out that here, the test and train was done on the same year, both in 2017. But if you look at the experiments like here, when we where we trained the network on SPDIF 17 and then used it for 2018, we got better results with RNN. And this is a visualized results. These are all the trained network on SPDIF 17, 18, and 19 using RNN LSTM network, and then used it for prediction on other experiments. So you can see that even when here, for example, we have negative R square, or here we have R square close to 0, it's only because we are using one-to-one method to calculate the R square, or this is, but like I said earlier, if we look at only which genotypes produce the maximum biomass, we can easily calculate that from the results here. Also, if we look, we can see that 2017 and 18, they are providing more close results, higher R squares, which means that the data in those 2 years are more similar, and the range of biomass is also more similar in 18 and 17. But if we look at 19 versus 18 or 17, we can see that the R squares are much lower because the range of the biomass is different in these years, and that's basically because the planting and sowing and harvest date is different for these experiments. So one problem we had with the first RNN network was that we could not consider having different number of data sets with LiDAR and hyperspectral data. We had to have the same number of data sets at the same time. But that's not the case, especially in our experiment. We had multiple data sets, we had different number of data sets on different dates. So what we did, we modified the network a little bit so we can have two different parts, one part for hyperspectral data, and the input vector would be consisted of hyperspectral and weather data. And the second part, which is similar to the first part, only the input is from LiDAR and weather. So this way we can consider having different number of data sets and also on different times. So from each part we have multiple neurons here, and then finally they all together predict the biomass. So we use that network RNN2, again with GRU and LSTM, but this time we used it for prediction of biomass multiple times during a season. So we had, like I said earlier, we had for hybrid calibration 2017, 2018, and test crops calibration 2019, we had multiple data sets in each season. So we were able to basically train the network so it can accept the input data from any time of the season and predict biomass for that time of the season, not only end of season. So here we can see that LSTM provided actually better results. So again, it's probably because it is more complicated. It has more parameters, so it can learn better. Here we are training and testing on the same experiments, so we don't need to avoid overfitting as much as we needed before. And for test graphs 2019, we had only 2 data sets, so the R square is lower than when we had 4 or 5 data sets. Another application of this RNN2 is that we can use it like, I would say, similar to a Kalman filter. So let's say that we have, for hybrid calibration 17, we have 5 data sets. We can train it on the first 4 data sets and then use it to predict biomass for end of season. So here you can see the results of each time we considered each date as test and other dates as train. So we train the network on for that one date as test. The same thing here. We can see that for 2017, if we use the 4 first dates for dates for training and then predict biomass for end of season, we could get around 12% RMSE. And for 2018, we got actually better RMSE for end of season prediction. And I think that that's because in 2017 we had biomass data collected sometimes in hand harvest, sometimes in machine harvest, but here we had most of the data collected big machine. So as a summary, first of all, we were able to train the networks for feature extraction and feature reduction in different experiments and use it for other experiments. It could be done unsupervised. And both fully connected one and convolutional one provided features with similar accuracy. For hyperspectral data, when we used feature extraction to the convolutional network, we found that it did provide better features when we trained it in supervised mode. With prediction models, we found that RNN1 provided more accurate results than SVR. And 2 was designed in a way that we could accommodate different number of data sets, and it was also capable of estimating biomass in multiple times during a growing season. So I have some suggestions for how to extend this research. First of all, we or whoever can look at transfer learning. We had these different experiments multiple years. We did not do much with transfer learning, but those techniques can be applied. We could look at incorporating crop models such as AppSim to generate augmented data if needed for some of the deep learning networks. We could extract some features from the whole season at the same time if we used RNN networks for feature extraction or feature reduction. We can apply the models in this study for multiple and or multiple traits such as LAI or even other crops. We think that with some modification we should be able to do that. I would like to mention that the parameter selection, hyperparameter selection for the networks here was done based on trial and error, but it could be done much better and basically model the behavior of each parameter. And finally, I think that we could investigate adding more input, more data sources, for example, thermal imagery, especially if we have drought or heat stress conditions. And also we could use soil information, soil moisture, for example. Those are important when we have multi-year, multi-location experiments, predictions. Here's a list of publications from the first 3 chapters. From the 3 chapters, I will have hopefully 3 publications. And if you have any questions, first of all, I want to thank you all for joining. Thank my committee. Thank Dr. Crawford, she's been amazing all along. I would like to thank all my friends, family, and everyone in trial meeting, professors, staff, students. Thank you.
So thank you, Ali. We really appreciate your presentation. So one of the things that I'd like to do, we are nearing the end of the first hour, would be to ask if anyone who's a participant but not a faculty member who's on the committee would like to ask a question. And you can do that. There's 2 ways. I believe you can raise your hand and I can recognize you. And the second is if you can come into chat, then you can type a question to me or say you can do it privately to me, to everybody, type the question or say I'd like to ask a question. Everybody's run out to grab some tea or coffee, maybe.
Ollie, this is Cliff. I've got a quick question for you.
Sure.
In your looking at all the hyperspectral data, given that you had sort of good to middling R-squared values, are there particular wavebands that look like they might be more useful to consider?
Yes, we did that actually in the first chapter. I don't have the results here, but we found that red edge and near IR bands, they are very important, and they sometimes if we used only those bands, we could even still get high R-square.
And do you know anything about what those bands might be useful in detecting? I mean, this gets more into biochemistry and plant physiology than might be your expertise. But
so those are, you mean like the nanometer, like which nanometer, which bands?
Well, which bands and what it is they're measuring, why they're useful.
So those are mostly 750, around 750, 700, 750 to 800 bands. And they are basically near IR bands and red edge. So what they do, so the reason that they are good for biomass is that different genotypes can have different reflectance on those bands. That's first reason. And also they are, I think that highly related to the stage of the growth, and also the greenness, the moisture content, to basically the photosynthesis of the plants, of the leaves. So they can provide very good R-square for biomass prediction.
Fair enough. Thanks a lot.
Thank you.
Any other questions? Okay. I don't see any on chat, and I don't see anybody raising their hand. So thank you very much, everyone. And so I will ask you to leave the meeting, and then the committee can remain and ask a few more questions.
All right. Thanks a lot. Good luck, Ali. Lots of work.
Thank you. Thank you all.
Nice job. Thank you, Ali. Good luck.
Thank you.
Okay, everyone. Click the lower right-hand part of your, wherever it is showing on your screen to leave the meeting. Everybody but Dr. Tynstra. Okay. I see him still on. Oh, here we go. Slowly leaving. Dr. Wang. Dr. Habib.
Amir Ali is my nephew. He can be.
Oh, he's your nephew. Okay, you can let him stay if he wants to. So, Ali has a nephew. How old is he? 11?
Oh, I'm afraid if I say something wrong, he's listening.
Oh, that's fine.
He's 11, yes.
Yes, okay. So whatever you prefer. So, maybe I can, let's see what I can do here.
I think he's trying, but cannot find it.
Okay, I can help him.